Welcome back. In this video we investigate surjectivity of linear transformations. Just as for injectivity, the concept of surjectivity is not limited to linear algebra. Suppose f is a function from a set x to a set y, then f is called surjective if for each element y of the set y, the equation fx is equal to y has at least one solution x in set x. As an example, consider the function from the real numbers to the real numbers given by fx is equal to x cubed minus 3x. The function grows to infinity if x goes to infinity and to minus infinity if f goes to minus infinity. Since the function is continuous, this means that any horizontal line intersects the graph of f. Algebraically, this means that the equation x cubed minus 3x equal to y has at least one solution for each real number y. This means that the function is surjective. Note that there may be more solutions than one, as can happen for some values of y. A counterexample is the function from r to r given by fx is equal to e to the power x. For negative y, the equation x to the power x equals y does not have any solution, so this function is not surjective. How does this work for linear transformations? We can easily translate the definition. Let t be a linear transformation from Rn to Rm, then we say that t is surjective if for each y in Rm, the equation tx equal to y has at least one solution x in Rn. Just as in the case of injectivity, we can tell whether a linear transformation is surjective or not from the standard matrix. Let T be a linear transformation with standard matrix A, then the following statements are equivalent. T is surjective and A has a pivot position in each row. Let me illustrate the theorem in two examples. First, consider the linear transformation T with this standard matrix. Is T surjective? By definition, that question comes down to the following. Does the equation tx is equal to y have at least one solution for each y in R3? We can rewrite the equation to ax is equal to y. Let's look at the augmented matrix of the equation. You can row reduce it to the following reduced echelon form. The stars on the right are combinations of the components of vector y. Precise expressions are not important now. What is important is that matrix A has a pivot position in each row. This means that the equation ax equals y is consistent no matter how you choose vector y. That is, the equation has a solution for any choice of vector y. So we find that T is surjective. Let's look at a slightly different example. Consider this linear transformation T. Is T surjective? Again, the question comes down to the following. Does the equation a times x is equal to y have at least one solution for each y in R3? Let's look at the augmented matrix of the equation. If you apply row reduction, you find that it's row equivalent to this matrix in echelon form. You see that matrix A has only two pivot positions. There is a row without a pivot. This means that the equation can be inconsistent. Indeed, if this element is non-zero, the equation has no solutions, and this can occur. For example, if y1 equals 1 and y2 and y3 are equal to 0. So for some choices of vector y, the equation has no solutions. Hence, T is not surjective. These two examples illustrate the theorem that I showed you before. You can tell whether a linear transformation is surjective or not from the pivot positions of the standard matrix. As was mentioned in the previous video, pivot positions are related to other properties of a matrix as well, such as invertibility. Therefore, surjectivity of a linear transformation is related to all kinds of properties of the standard matrix too. You will learn more about such relations in the rest of the section.